Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills, so sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 3.31. The problem statement says, the reaction A to B is carried out in a laboratory reactor. According to a published article, the concentration of A should vary with time as follows. Where CaO is the initial concentration of A in the reactor and K is a constant. Part A, if Ca and Ca naught are in pound moles per feet cubed and T is in minutes, what are the units of K? Well, in order to do this problem, you have to remember that the exponent term cannot have units. Therefore, Kt, the inside of this, cannot have units. Well, T does have units, so K needs to cancel those units. Okay, so for part A, they told us the units of the different components of this equation, and we need to find out what the units of K are. So the only thing that we know right now is that K times T has to be unitless. So we set up our dimensional analysis here. We know that K times T units needs to equal to 1 because that is unitless. Well, we can just use algebra now to solve for what the units of K are by dividing both sides by minutes, and we get that the units of K are equal to 1 over minute. Part B says the following data are taken for Ca as a function of T. Alright, let's move over to the computer for this part. Okay, we moved over to the computer and I've replicated the data that they gave to us in this section. The problem statement continues. Verify the proposed rate law graphically. First determine what plot should yield a straight line, and calculate Ca0 and K. Okay, so we need to set up our model. So let's jump back to our writing here. Okay, so it's our job to create a linear model, and then from the linear model we'll calculate, from the linear model and the data we'll calculate what the two parameters are, Ca0 and K. Alright, because this term has an exponent in it, that's a good sign that you should, in order to turn this into a linear equation, you just take the log of it. And if you take the log of both sides, you'll be able to eliminate the exponent term and make something that looks more like a line. You take the log of both sides and you're left with this equation that looks a lot more like a line. So now we can write down what our line model is. Alright, so our line has a y variable, which is the natural log of Ca, an x variable, which is t, and a slope, and an intercept. Alright, so now let's move back to the computer and program our model into the computer. Alright, so for our model, we need to program what our y-axis is, what our x-axis is, and then we need to calculate what our parameters are based off of the x and y data that we have. Okay, so according to our model, y is equal to the natural log of Ca. And x is equal to t. Okay, so that's it for our model. Now we need to program the parameters. M is the slope, known y's, known x's, and b is the intercept, known y's, known x's. Okay, so we've programmed our model here, So now we need to calculate what CA naught and K are. And according to our model, CA naught is equal to the exponent of the intercept. And K is equal to the opposite of the slope. Okay, so that is our model and what the parameters from our model equal. So that gives us a good estimate of what CA naught and K are. All right, so let's move back over to our writing here. All right, so that is it for part B. Convert the formula with the calculated constants included to an expression for the molarity of A in the reaction mixture in terms of T seconds. Calculate the molarity at T equals 200 seconds. Okay, in order to change this function into molarity units and second units, we need to change our parameters into molarity and seconds. So for part C, all right, I've written down what we're supposed to do for part C, and now let's start with the concentration and turn that into molarity. All right, so we need to take our CA naught in terms of pound moles per feet cubed, and we're converting the units over into moles, gram moles per liter, which is units of molarity. Okay, so then we take our second constant, it's K in per minute, and we convert that into K into per second, and this is the new K value. So now we have our new CA naught value in molarity and our new K value in per second. And we just use those in our equation. All right, so now we make sure we use the right values for K and CA naught that we just calculated. And we can plug 200 into this equation and calculate what CA equals after 200 seconds. All right, and that is the answer to part C. And that is it for problem number 3.31. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.